Okay, we are back at it. Let's get through chapter 10. It is a meaty chapter. So this is going to be one of our longer videos. I've got a shot glass filled with chocolate chips for energy. Let's go ahead and get started. Cat, you might have to move. All right. Chapter 10 is all about circles. We started off with some basic definitions, what a circle is, the set or locus of all points who are equidistant from a set point called the center, and in a given plane. If you don't say in the given plane bit, you might end up with a sphere. We've talked pretty much all year about some of these things, like radii, the center. We talk a little bit about concentric circles here, real formal about the interior, the exterior. We mentioned what a diameter is and what a chord is. A chord connects two points on the circle. Additionally, they give the formula for the area and the circumference, both of which involve pretty much the same players. One of them, the circumference, equals 2 pi r, or pi d, and the area is pi r squared. Confusing because this one has a 2 and that one has a 2. One's a coefficient, one's an exponent. They both have pi's, they both have an r. Always remember that when we're looking for the area of something, it's one dimension, which is a radius, times another dimension, which is another radius here. Technically speaking, we could do pi d squared over 4 and get the same answer. Nobody ever uses that formula for reasons I don't know. A lot of this chapter is theorems and their converses. For example, we have a theorem that says if a radius is perpendicular to to a chord, then it bisects the chord. And I'm going to put a little caveat in here, a little extra bit. I'm going to say, or part of a radius. Hi, if a radius or part of a radius is perpendicular to a chord, then it bisects that chord. Of course, the converse, the very first things we did this year, should say, if a radius bisects a chord, then it is perpendicular to the chord. And those were 2 out of the 3 theorems in section 10.1, but they're the only 2 that we did. We did a lot of problems, which they would give me a chord, maybe its length. They would give me part of the radius, basically its distance from the center. We always measure distance perpendicularly. It's the shortest distance. And we would look for the relationship between the radius, that distance, and the chord. Well, this is half of the chord, and that, of course, forms a right angle. So you can use Pythagorean's theorem. If you know 2 out of the 3 of the things, you can find the third. I felt like those problems had a moral to them. And the moral was you only got one answer. If you were looking for the distance and you knew the length of the chord, you only got one answer. And so that told me that if I had another chord, which were the same distance, which was the same distance, then it would have to have the same length. And that brings us to 10.2 and the 2 theorems there, which again are converses of one another. If 2 chords are equidistant from the center of a circle, then they are congruent. And of course, the converse, which says if two chords are congruent, then they're equidistant from the center of the circle. In 10.3, we started talking about arcs, arcs being part of a circle, arcs having two different properties. We were talking here about the measure of an arc. And we mentioned that the measure of the arc is equal to the measure of the central angle. So if this were 60 degrees, to turn my pen from there to there, it would turn 60 degrees. Well, if I walked keeping my left shoulder against the circle like that, I would have also turned 60 degrees. So the measure of an arc is equal to the measure of the central angle. And that brought us to what I'm going to call the congruency bonanza. These 6 theorems on page 453, which all say very similar things. They all say if blank are congruent, then blank are congruent. And you could fill in the blanks with central angles, chords, or arcs. At about this time, it's appropriate that we mention that any number of theorems that we've dealt with way back in the past involving segments or angles are also valid for arcs. So for example, if an arc is added to congruent arcs, then the results are congruent. If congruent arcs are subtracted from congruent arcs, we can talk about the midpoint of an arc, bisecting an arc. It works exactly the same way as everything else. Okay. 10.4, we talked about what a secant and a tangent is. A secant is a line which contains a chord, and a tangent is a line which intersects a circle in exactly one point. So this over here is a tangent, and this is a secant. Secants, in my opinion, are only interesting because as they get closer and closer to a tangent, they act more and more like one. And we can actually discover some of the behavior of tangents by looking at extreme examples of secants. However, our focus is going to be entirely on tangents. We have a couple theorems from 10.4. We have one which says, if a tangent intersects a radius, then they are perpendicular. So if that is a radius starting from the center of the circle, regardless of how bad I drew it, then it should be perpendicular to the tangent that it touches. And there were a couple of problems that we dealt with at this point. We dealt with common internal tangents, common external tangents, and walk-around problems. To do a walk-around problem, you really have to take advantage of this other theorem, which says if two tangent segments, which I will usually just refer to as tangents, come from the same point, then they are congruent. So if I draw that guy and that guy and claim that they're both tangents, they would have to be congruent to one another. I'm not going to go through the common tangent procedures. They are pretty specialized, as is the walk-around problem, but it is something which is not a bad idea to review. Okay, 10.5 was a big deal. 10.5 was where we started looking at how angles relate to arcs. And basically, there are 3 main categories here, where the vertex of the angle is in the circle, where it is on the circle, or where it is outside the circle. So if you are in the circle, you have 2 choices. You could either be a central angle where the vertex is literally the center, at which point if this has a measure of x degrees, then the arc has a measure of x degrees as well. And it doesn't make the other one wrong. If I kind of continue in these lines, well, that's a vertical angle, it'll be congruent, and this guy will be x as well. But in general, what if you are not at a central angle? If your vertex is just somewhere in the circle, I'll draw the center of the circle someplace else to illustrate that it's not the center of the circle. And this were x, this is A, this is x again, it's a vertical angle, and this is B. Well, x, the angle, is the average, what I get when I add the two arcs together and divide by 2. X is the average of the arcs. The common mistake that I see when people do these problems is they just take the first two numbers that are given, add them together, divide by 2, and say that that is the answer, which oftentimes we won't give you these two arcs. Maybe I'll give you this one and something to help you find that one. I don't know, or maybe I give you an arc and the central angle. You don't add those. So please don't do that. All right. On the circle, these are greedy angles who are always trying to eat something double themselves. If this is x and this is a, then x is 1/2 of a, or a is 2x. Either way you want to fly. This case is called a chord because the angle is comprised of two chords, but it works just the same if it is a tangent chord. So there's x, there's a. The last one is outside the circle. And there are a few varieties of this. There is the tangent case, which is a special case, and I'll do that one last. There is, of course, a tangent secant and a secant. And the same formula works for all of them. If I call this x, the bigger one a, the smaller one b, x, the bigger one a, the smaller one b, that's kind of the least efficient way I could have done it, then x is always equal to a minus b over 2. It's true for this one, the tangent as well, but special case, x plus b add up to 180. I always incorrectly say that x and b are supplementary, although it gives the right idea, it's kind of the wrong word for that. So there is 10.5. 10.6 is 3 shortcuts, one of them is right here, based on the same thing. 10.6 says that if an angle is inscribed in a semicircle, then it is right. In other words, if I had a semicircle, so there's a the center of the circle right there, and I pick anywhere here and connect it to that point and that point, I must have a right angle. After all, its vertex is on the circle, so it's one of those greedy angles trying to eat something double its size. Well, a semicircle is 180. If 180 is double its size must be 90. As we pointed out, the tangent angle is supplementary, and the other 1.5 theorems really said if two angles whose vertex is on the circle are trying to eat the same arc, intersect the same arc, then they must be congruent. Or if they're trying to, so that angle and that angle are both eating the same guy, they must be congruent. Let's see what I was doing right there. This angle and this guy are both trying to eat this one. Or if they intersect congruent arcs. So if I did something like that and marked this guy congruent to that guy, then yes, again, they would have to be congruent. As I said, a lot of stuff in chapter 10. But we're getting there. 10.7 talked about inscribed and circumscribed polygon. Polygon is inscribed if it's inside the circle, and a polygon is circumscribed. Excuse me, I said that one wrong. No, I didn't. Inside the circle, inscribed. Circumscribed about, then the polygon is on the outside. And we had two theorems here. One which said that if a quadrilateral, any quadrilateral, doesn't have to be anything in particular here, this guy is inscribed in a circle, then the opposite angles are supplementary. So any of these two opposite angles would have to be supplementary. Just to show you, this one looks to be, I don't know, maybe about 60 degrees. So it should be eating an arc, which is 120. If that's 120, the rest of the circle should be 240, and the rest of the circle is being eaten by this angle, so it has to be half of 240, it has to be 120 again, and notice that those two things add up to 180. The second theorem is kind of a corollary, depends on this one, and it says if that quadrilateral that was inscribed wasn't just a generic quadrilateral, but was in fact a parallelogram, then it's going to be more than just a parallelogram. It is going to be a rectangle. We know for any parallelogram that opposite angles are congruent. We've just shown that the opposite angles must be supplementary. If you are supplementary and congruent, then you are right, and a parallelogram with right angles is, of course, a rectangle. And the next thing was the power theorems. There were 3 of them, and we did 1. That one was the chord power theorem. It says that A times B equals C times D. We proved it when we did by creating similar triangles. Notice that that angle and that angle are eating the same arc. They've got to be congruent. This angle and that angle are vertical. We've already got AA. Well, A times B equals C times D comes quickly from the triangles being similar, their sides being proportional, and if a proportion exists, then you can cross multiply. That's the only one of those that you need to know. Finally, we brought it back around to arcs, and we talked about their other attribute aside from their their measure, which is the arc length. So if this is a circle which has a radius of 3 inches, then to walk from there to there is not particularly far. If it's 3 miles, then that's a decent little walk there. So what we did was we put in a radius and a central angle. I don't know, looks to be about 80 to me. And we came up with the proportion that the central angle is to the central angle of the full circle, 360, as the arc length, we'll give it an L for arc length, is to the arc length of the full circle, well, that's really called the perimeter, and that's 2 pi r. In this case, I would say that 80 is to 360, as my arc length is to, looks like 20 pi. Okay. And then we can solve from there. In chapter 11, we did something similar and related to find the area of a sector. We can leave that for area. All right, next up, chapter 11 and 12, we'll probably do them in one go.